Oh, all right, guys, I think I'm gonna go ahead and get started. Thanks for coming down today. It's nice to just come in and park easy and nice close parking spots on the weekend is always nice. And hope that you're having a nice weekend and enjoying the calm before the storm, I guess we could say. The next 2 weeks gonna be kind of crazy time, I guess. But yeah, we are in good shape for the 250B. Don't forget that there is an extra credit quiz that is due tonight, actually, at midnight. So a few people have turned it in already, but there's still a ways to go on that. It's a win-win because it will help you study for the midterm and you'll get extra points towards that midterm. So I would definitely recommend doing that. The other big thing that I would recommend doing probably relatively soon would be at least to try a sample test. There are 2 of them in the midterm 3 resources folder, and you want to leave yourself enough time that if you take one of them and it's like, oh my gosh, I need to review X, Y, and Z, that you have enough time to actually do that. So I would not wait too long, much longer, because it's only 2 days until Tuesday now. I would not wait too much longer to try one of those sample tests. And then depending on how that goes, you might even decide you want to try the second one also, just to really make sure you're solid on everything. I would recommend those things as a priority. Also, the group works would be good to go over. You probably cannot review all of the homework again, but of course, if there was a certain assignment that you didn't really feel as comfortable about, or that maybe you just didn't even have time to give it your best thoughts, you could look back and spot check certain things from the homework, but I would probably focus more on the sample tests and the group works. The stuff that's in the resources folder as well could be useful, and the problems that we're going to do right now today. So I think that'll be good. I accidentally printed out about 15 copies of the questions we're going to go over. So some of you have that in front of you here, but it's the same thing that's in Canvas. So don't feel deprived if you don't have that handout in front of you. I have 11 problems, I think, on that sheet, and 10 or 11 problems, and I'm going to not go in order. I'm going to jump around a little bit. And I am actually going to start off by giving you guys, since you're here in person, a freebie question that's not even on the sheet. So I'll call it problem 0 as a nice warm-up problem. Also, I am recording this review and I will be sending it out later today. If you need to leave early, or if you just need to rewatch something later, if you feel like you need a little bit better review of something, you'll certainly be able to do that. But as always, guys, I totally welcome questions. Don't be shy. If you have a question, you're not sure on something, there's a very good chance in a class this big that there will be others with the same kind of questions. So they would probably appreciate it as well if you ask those things. Okay, so I'm not on any big agenda to rush through this stuff. I want to really make sure that we learn it well. So make sure you slow me down and ask questions as we go along. But let's try, just right on cue, let's just try, I'm going to call this problem 0. And this is a theoretical problem. And it says the following: if A, which is n by n, is diagonalizable and invertible. Okay, so this one is not on the handout, but if A is diagonalizable and invertible, show that A inverse is also diagonalizable. Okay, so this is a fresh question. It's not in any of the materials that we have. And before I do it, this might be a good time to make a plug for group work number 11. That was one of the group works that we've had. In this group work, we gave examples of matrices that were invertible but not diagonalizable, and then also matrices that were diagonalizable but not invertible. So these 2 things are unrelated concepts, really. You can have matrices that are one without the other. But if you have a matrix that is both diagonalizable and invertible, then the inverse matrix is also diagonalizable. So if you didn't know how to maybe do this problem, let's say it's a 5-point problem or something, the solution is very short, by the way. If this is a very short problem, what you would want to do, test-taking strategy, write down as much as you know and see where that gets you. Like, do you know what diagonalizable means? Because that would be part of what you're going to need to be able to solve the problem. So try to write down the things that you do know. Sometimes I'll see people just write this equation down, AV equals lambda V. We are going to see this in one of the other problems in a little while. And of course, this is very important, and I've talked a lot about it, but if it's not really relevant to the question, I probably won't feel too compelled to give a lot of partial credit if it's not really what the problem is about. And in this case, this is not what this problem is about. It's really more about the big picture of having a diagonalizable matrix. Can anybody remind me, or do you want to start me off with any ideas on what might be relevant here that we could write down to kind of get us started? So diagonalizable, what does that mean again? A is diagonalizable means, now we're getting onto something that is actually relevant to the problem. Can somebody remind me what the definition was?
Is that when the eigenvalues pull their weight?
Yeah, all of the eigenvalues pull their weight. And in other words, there are a total of n linearly independent eigenvectors. I should have mentioned that A is n by n here. So the number of eigenvectors would be n. So you have n of those. And what do we typically do? So if you wrote this down, by the way, you would get partial credit for this, even if you didn't write anything else down. Okay, so tell me everything that's relevant that you know. This is certainly important. What do we typically do once we have these n linearly independent eigenvectors? Like, what kind of homework problems have we done? Or what's the whole point of this? Like, if I have a diagonalizable matrix, so what? What do we do with it?
General solution.
There's no differential equation system here, so it's not really that. I mean, you guys have all done this, so I know you know the answer. It's just I'm not prompting you. What's that?
The S and the D.
The S and the D thing, right? Yeah, I would want to think of, like, normally. In fact, for those of you who've done the take-home quiz, the very first problem is, here's a matrix. Is it diagonalizable or not? If it is, find S and find D, right? And what was the relationship? So then we have, let's write it down. We have S, which is n by n, and D, which is a diagonal matrix. It's also n by n. They're both n by n matrices. With S inverse AS equals D. And just to be clear about this D, I'm sure you guys remember that the diagonal is filled up with the eigenvalues, the lambda 1 through lambda n, like that. Okay, so this is where lambda 1 comma lambda 2 dot 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 up to lambda n, they're all the eigenvalues of A. Right? And if you want to be really thorough, which would be a good idea here, you could write down the S has columns that are consisting of the corresponding eigenvectors. So just knowing all of that theory allows you to just put this down. There's nothing up here on the board, guys, that is new to us. This is basically just the big deal about a diagonalizable matrix. So if that's true about A, so A was assumed to be diagonalizable, so we have all this stuff, they're asking us to show the same thing about A inverse. So in other words, is there an S and a D for the A inverse? And if so, like how could we get it? Would be the question. This is really the key equation here, in fact. Anybody want to propose how we can take this equation does not have A in it, does not have A inverse in it anywhere. Could we somehow make an equation that would have the A inverse in it though?
Can we multiply both sides by A inverse?
So multiplying both sides by A inverse, maybe I'll scribble here for a second. Yeah, so doing some kind of algebra sounds like a good idea. So like I could multiply through by A inverse. I don't know, so maybe something like this, A inverse S inverse A S equals A inverse D, something like that. That at least brings the A inverse into the problem somehow. And can I do anything with this? Not sure. The goal is actually to create another equation like this, but with the A inverse in the middle of it. And when I did this process here, I didn't really get the A inverse into the middle of what I was working on. I got it kind of stuck over here on the left. Would there be a way to get the A inverse into the sort of sandwiched between a matrix and its inverse just from this? Seth?
Multiply both sides by S.
Okay, so we could now try to multiply both sides by S. So following up on Reed's suggestion of multiplying through by A inverse, we could also try to multiply by S. Now, if I do that, this is getting kind of long, but let's just check it out as something looking kind of like that. Yeah. And I do have the A inverse sandwiched between S and S inverse right here, which is kind of the idea. I have all this other junk that's kind of in the way. Maybe I can like move the other junk to the other side just to get it out of my way. So if I solve for SA S inverse here, right, that would require me to first write multiply on both sides by S inverse and then write multiply on both sides by A inverse. So I could do that. And that sort of gives me this thing. But the problem is, like, this would need to be still a diagonal matrix. And I don't really see that it is. It's not obvious to me that it is a diagonal matrix. So I'm just still not quite sure. Is there another, instead of left multiplying by A inverse and then left multiplying by S, is there a different algebra step we could take with this very first box equation here instead? That might work.
Can we multiply by S initially for that? And then,
You want to do the S first.
yeah,
So S times S inverse AS equals SD, so that you can cancel.
Yeah.
That's true. And then I could actually solve for A by right multiplying by S inverse, like so. It's still not quite what I was thinking of, but it would work, but there's something easier we can do just directly from here to both sides of this equation. Instead of multiplying through by something, can I do something else to both sides of an equation? Is that a hand? Okay. Anybody want to try? It's a little tricky. Let me show you what I have in mind. I'm going to go ahead and erase this one. What you can do, guys, is you can take that box, and it's very simple. You could just take the inverse of both sides. So you could literally just say S inverse AS quantity inverse is equal to D inverse. This is what I had in mind. This is the trick. This is actually the trick. And do we know how to have an inverse of a product simplified? If I have a bunch of matrices multiplied together and I take the inverse of that, is there anything we can do to, does anybody remember a formula for the inverse of, say, two matrices that are multiplied together? What is this equal to?
Identity?
Sorry?
The identity?
No. I'm just looking for something on this side that would be the same as the inverse of the quantity xy. And this we definitely did in class. It was months ago, though. What would I have to multiply xy by to get it to cancel to the identity? Well, this is good. We're reviewing this. This is really chapter 2. The formula for this, guys, is the inverse of the individual matrices in the opposite order. So remember that the order of matrix multiplication matters. We have to keep track of that. So in this case, the inverse of the quantity xy is y inverse x inverse. If I apply that here on the left side of what I have, what it means is I'm going to take the inverses of the individual matrices here, but in the reverse order. So the one on the right comes first, and that would be an S inverse. And then the one in the middle would be an A inverse. And then the one on the right would be the S inverse inverse. And this would equal D inverse, like that. Yeah. What is S inverse inverse? It's just S, right? So this becomes S inverse A inverse S equals D inverse. And guys, D inverse, does anybody have a proposal? What would be the inverse of this matrix? This is D right here. What would be the inverse of this? Like, what would you have to multiply this by in order to get the identity matrix?
I know. My
This specific matrix. So just don't worry about any A or S or anything. Just if I have this diagonal matrix, what's the inverse of it? Like, what's the inverse of the matrix 1, 2, 3? And if I just have a diagonal matrix like that, what do I have to multiply this matrix by if I want to get the identity matrix? One more time. I don't think so. Let's try it. 3, 2, 1. If I do that, then when I multiply this out, 3 plus 0 is 3, right? It's actually not going to give me, I think it's actually going to give me 3, 4, 3. I would like to get 1, 1, 1 on the main diagonal. So what numbers do I need, Chris?
1/2
That's right. 1/2 and 1/3. That's what we need, right? So sorry, this should have been, this is 1, 2, 3. This over here should have been 1, 1/2, 1/3. The point being that the D inverse here is 1/λ1, 1/λ2, and ... down to 1/λn. Zeros everywhere else. That's the inverse of the matrix. But the point is, it's still a diagonal matrix. And do I have to worry about any of these lambdas being equal to 0 that I have on the bottoms of those fractions? Would that ever happen in this case? What do we know? Yes.
The determinant cannot be equal to 0, so and below n cannot be equal.
Exactly. If you multiply all of the lambdas together, you get the determinant of the matrix, which would be not zero, right? So the determinant of A is not zero, and all of the lambdas are multiplying together to create the determinant, and that would be not zero. So none of the lambdas are zero, so I'm perfectly safe in dividing by any of them that I want. But guys, this equation has A inverse sandwiched between a matrix and its inverse. It's actually the same matrix and the same inverse that we had before, but with a different diagonal matrix. So this is exactly what it means to show that A inverse is diagonalizable. Yeah, so that's it. That's what I would be looking for. That's exactly what I would be looking for. Actually, follow-up question. While we're thinking about these theoretical problems, and then I promise I'll get away from it for a little bit. Can you prove that fun fact? So if the eigenvalues of A are lambda 1, lambda 2, and dot, 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 up to lambda n, prove that the determinant of A is the product of the lambdas. Wonder if we could actually prove that one. We keep using it. This is what I usually call fun fact number 2. The fun fact number 1, which you should also know, is the one where you add up the lambdas and it gives you the trace of the matrix. This is fun fact number 2. If I multiply my lambdas together, I get the determinant of A. Does anybody think that they have an idea how I could actually show it? Because I've been using it without showing it this entire semester. We actually have everything on the board. The reason I'm doing this right now is everything we need to understand that point is already on the board. In the blue writing somewhere. So we have this equation here, right? So what could we do with this equation that might be helpful for proving something about the determinant of A? I have this equation. Anytime you have two matrices that are equal to each other, what's one thing you can always do to both sides of the equation? I heard it.
Take the determinant.
Yeah, you can just take the determinant of both sides, right? So in other words, given S inverse AS equals D, we would have the determinant of S inverse AS equals the determinant of D. That is so true. That is so true. And let's work on this a little bit. Does anybody know any properties of determinants that we could use on the left side here? If I have a matrices multiplied together and I want to take the determinant, do we know any properties that we've maybe learned? Ryan, yes.
You can separate it into a determinant of S inverse times determinant of A times determinant of this.
Beautiful. Exactly. This is one of the properties of determinants that we learned back in chapter 3. And so we can absolutely do that. And so I'll still write determinant of T over here. And does anybody remember how the determinant of S inverse is related to the determinant of S? This is good review, not only for chapter 7, but really for our final the next week, because we're reviewing some stuff about determinants here. The determinant of the inverse of a matrix compared to the determinant of the original matrix, what's the connection?
The same.
They're not the same. The same would be like if we did a transpose, that would be the same. Or if we did the A operation of EROs, that would be the same. But in general, the determinant of S inverse is not the same as the determinant of S. What was the formula? Do you remember?
Is it 1 over the determinants?
That's right. That's right. This is 1 over the determinant of S. Right? So this is 1 over the determinant of S. Exactly right. That gets multiplied by the determinant of A and then the determinant of S, right? So that's absolutely what we want to write down. And here, you are just looking at a bunch of numbers. So I always make a big fuss about not switching the order of anything. That's when we have the matrices in front of us. But as soon as it's a product of numbers, guys, we absolutely can cancel the S with the 1 over the determinant of S because those are just numbers. So the determinant of A, therefore, is equal to the determinant of D. What is the determinant of a diagonal matrix?
Just diagonal multiply.
Just multiply the diagonal together. That's exactly right. So the determinant of D is just lambda 1 times lambda 2 and ... times lambda n. So there you go. The determinant of A, which is equal to the determinant of D, is the product of the lambdas, which is this fun fact that we've been using over and over again ever since chapter 7. Now we at least see the proof of it. We have a little bit of a proof of that. Okay, so of course I'm going to ask you the questions on the exam. You know, here's a matrix, find S and find D. But it's easy to kind of get very mechanical in the process and not really be thinking about what's going on. So a question like this or the follow-up sort of forces us to conceptually remember what's really going on there. So I just wanted to start off with a little free extra question that is a little bit more conceptual than what you sometimes will see. What do you guys think? Is that all right with everybody? Yeah, Reed.
Can we expect more conceptual questions on this midterm, just like other?
I don't know.
Okay.
I've not written the test yet. That's the only thing I can tell you. And I have no idea. You just take a look at the samples because I usually try to make my sample test at least modeled off of kind of past examples, but I don't know for sure. Yeah, I might, I might do something where you only have to do a certain number of them, or I might just give you a freebie problem. So like I understand with these conceptual problems, sometimes if they just don't hit you quite right, then you're kind of like not sure what to do. So I'll try to be a little bit nice about that. But I do want you to be able to do some of these conceptual problems for sure. Okay, let's change gears. I'm going to give you another problem. So I'm going to go out of order on the handout. So I'm going to actually jump to number 3. I'm going to do something that's more computational next, and then we'll come back. And this one just asks us to solve the general solution to x prime equals a times x, where the matrix A is the following matrix: -1, -4, -2, -4, -5, -6, and 4, 8, 7, like that. And there is a hint. I'm going to give you a hint that there is a lambda of 1 plus 2i. That is one of the lambdas. You'll notice that this matrix does not have any zeros in it. If I was to actually work on the characteristic equation for this, I would subtract lambdas off of the main diagonal, but it would be computationally a messy cubic equation that we would end up with. Probably too much for me to put that on the test. So what I would be more likely to do would be to give you a hint of somehow giving you the lambdas. Now here I did not give you all of the lambdas. And there's a reason that I only gave 1 lambda here, is because I actually think that based on that, you guys should be able to come up with the others. How many lambdas in total would I have for this problem? 3 of them, right? So I've only given you one of them. Let's just call this lambda 1. What would be, can somebody tell me what one of the other lambdas would have to be? So now we have to figure this part out for ourselves. Go ahead, yes, Michelle? 1 minus 2i, because they come in complex conjugate pairs, right? And then would we be able to figure out the third lambda now that we have that?
Mhm.
We have our fun facts, right? And the easiest fun fact is actually not this one. It's the one about the trace. If you add up the main diagonal of this matrix, it adds up to 1, actually. -1 plus -5 plus 7, it's 1. So your 3 lambdas should add up to 1. Now, if I look at what I have so far, they are adding up so far to 2. So to make the fun fact work, what does the third lambda have to be? -1, right? If you now add up these lambdas, you get 1, which is the sum of the diagonal values. So those are your lambdas. Those are the lambdas. And by the way, is this matrix defective or not defective, or we don't know yet?
Non-defective.
It's not defective. Why do we know that it's not defective?
Because there's no repeat.
There's no repeated lambdas, exactly. So very good. Non-defective, I'm gonna write that down now. If there had been a repeated eigenvalue, then it would maybe be defective, but there's no guarantee, right? There would be no guarantee in that case. So we would have to explore the eigenvectors to figure that out. Yes, Seth?
We're adding them together with imaginary numbers and stuff that adds up to 2, because are we just imagining they're not there? Or?
Well, the imaginary numbers are always the imaginary parts of these numbers will always cancel, because you'll have a plus bi getting added to a minus bi. So the 2i and the -2i cancels essentially, and then it's really just the real part that you're working on. Is that what your point is? Yeah. So that's a good point. We don't really have to think too hard about the imaginary part there. Okay, let's go and work on these eigenvalues. Which one do you want me to work on first?
The harder one.
The hardest one first? I like to do that too. You know, whenever I go out climbing mountains, if there's gonna be more than one mountain on my little climb, I always do the hardest one first. Cause I'm like, if I don't do that, I'll run out of energy. I won't be able to do the rest of them. So yeah, let's do the hardest one first. I personally think the hardest one are the ones involving imaginary numbers. So I'm gonna start off with the lambda 1, which is 1 plus 2i. And we're gonna try to find the corresponding eigenvectors now. And that involves calculating a null space that is associated with that eigenvalue. So we'll write down null space of, and now I'm going to subtract 1 plus 2i from the main diagonal of A, right? So we take the matrix A, we're going to subtract the lambda value off of that diagonal. So I have to subtract 1 plus 2i. So it's going to be -2 minus 2i, and then -4, and then -2. And then on the second row, I have -4, and then I have, let's see, it's -5, but I'm going to be subtracting 1 plus 2i. So that's -6 minus 2i, and then -6. And then on the bottom row, I would have a 4, and then an 8, and then I have to subtract 1 plus 2i from 7. That's going to be 6 minus 2i. There you go. There you go. This looks awful in terms of trying to solve it, but you know what? We are gonna do it pretty easily. We're gonna solve for the unknowns, the x, y, z. We'll solve for the x, y, z actually easier than you think. The first thing to remember is that this matrix cannot be invertible, which means that if you did EROs on it, there would have to be a row of zeros that emerges, which means that we can basically, we know for a fact that one of these rows would get wiped out. And so I'm perfectly okay if somebody wants to suggest does anybody have a particular row that they think they would like to wipe out? Row 1, row 2, or row 3? 3? 3?
Yeah.
3, 3. Well, I wanna wipe out row 1. Is that okay? Do you wanna write row 1? Yeah, why do you wanna wipe off row 1?
So the two cats, or like the -4.
I see the -4 and the 4, and I know if I add those together, if I just do the ERO or I add them together, I'm gonna make a 0 there. Yeah, actually, if you had wiped off row 3, it would have been okay. But it's actually easier, in this case, it's actually easier to just get rid of row 1. Of course, it would not be wrong to cross off row 3. Are you allowed, by the way, to always just blindly cross off any row? That's a bold answer. Let me try you out on a matrix here. What if my matrix was 1, 1, 1, 2, 2, 2, and 3, 4, 5? And that was my null space matrix. And I said, yeah, I know that I have to be able to cross off a row, and then you come along and cross off that row. Would that be good? Probably not. Probably not, because actually it's the first 2 rows that are multiples of each other. So one of those first 2 rows could safely be crossed off for sure. The third row, I'm not so sure. So how do you make sure you don't cross off the wrong row? There is a foolproof method, at least for 3 by 3. The foolproof method, guys, is that you'll know that you crossed off a good row to cross off as long as the other 2 rows that are left over are not scalar multiples of each other. So like right here, these 2 rows would have been scalar multiples of each other, which means I didn't cross off a row that would turn into 0, 0, 0. So I just have to look at these 2 rows and just convince myself that they are not scalar multiples of each other, and that's good enough to confidently cross off row 1 and know that it's okay to do that. I've never really made this point before, but it's worth mentioning. You can't just arbitrarily cross off a row. Now, if it's a 2 by 2 matrix, then the 2 rows are for sure multiples of each other, and you can cross off either one. It makes no difference. But for a 3 by 3, you just have to be a little bit cautious. Okay. Anyway, are we okay so far? Yes.
Wait, how are they not scalar multiples of each other?
These 2?
Yeah.
Well, I can't take the second row and multiply it by a constant and get the third row. Because I can see that in order to make the second row match up to the third row, I would have to do just a sign, just because of the -4 and the 4, I would have to just make a sign change.
Oh.
And if I just make a sign change on the rest of that second row, I'm not gonna get the third row. So that's all. Okay, so guys, I have crossed off row 1 against all of your advice. So we'll see if this works out. Now, Dante made the point, and he's right, that if I add these 2 rows together, I'll create a 0 into that third row. So I'm actually gonna do that right now. I'm gonna recopy row 1. I'm sorry, well, row 2 is now going to become row 1, and I'm going to add the 2 rows together and put that down next. So -4 plus 4 is 0, and then -6 minus 2i, I add 8 to that, I get 2 minus 2i, and then when I add -6 and 6 minus 2i, I get -2i. And then, as I said before, the other row has basically been wiped out as all zeros. At this point, I can essentially circle a couple of pivots into my row echelon form. My unknowns here are x, y, and z. And the problem is these aren't really pivots. As you know, a pivot technically has to be a 1, and I don't have them as 1s right now. So even from here, you know, I could say, okay, you don't need to write this down because this is not what I'm going to end up doing. I could just say that z is free, which is t. But if I did that, then I would have to solve for y by using this second row. This is really what the middle row of the matrix tells me. And if I put in t for z, and then I try to solve for y, I'm gonna have to do something that I really don't wanna do. I've never done it before. You've never seen me dividing by complex numbers before. It's not that that's impossible to do, but it's a mess to divide by a complex number. So I am gonna try to avoid that. And I am wondering if anybody has a suggestion for how I can get my eigenvector. I want to get my XYZ without doing the free variable thing. Did we have any other tricks that we ever learned for finding the eigenvector here? Read. Yeah, you were just in my office. And we had a 3x3 matrix where we were hoping to use that AB trick. Do you guys remember the AB trick? If I have just two numbers in a row of a matrix and I want to write down a vector, the vector can be chosen as just negative B and A. Now, the problem is this doesn't look like it's a 2x2 system. However, if I focus only on the second row, it is, because the X is not there, right? There's really a 0x in that second row. It's not really one of my variables that I'm going to be solving for in the second row, is it? So I actually, guys, I can do this AB trick that I keep talking about. I can do it just on the Y and the Z. So I can swap the two and then make a sign change on one of them. So this negative 2i, I'm going to write it as 2i, and then the 2 minus 2i gets swapped to the bottom slot. That becomes your y and your z. Now the x, we haven't solved for that yet. I still would have to figure out x by going back to the first row. Are you guys with me? They aren't always this messy. I'm just trying to make sure that I give you a sufficiently complicated one that you would be able to handle something like this. So going back to the first row says negative 4x plus negative 6 minus 2i times y minus 6z should add up to 0. This is from the first row, right? But I've already figured out what y and z are. So I can already put in the y is 2i and the z is 2 minus 2i. And I bet I'll be able to solve for x now. Let's try it. Let's try it. So I have negative 4x and then plus negative 6 minus 2i times 2i. And then minus 6 times 2 minus 2i adds up to 0. That becomes my equation where I put in what y and z are already. And I'm going to have to mess around with the algebra here for a second. Negative 4x, I'm going to distribute these later terms totally out. This is going to be minus 12i. And then this is minus 4i squared. But remember that I squared is negative 1. So there's really a 4 with a negative 1, and then there's a minus in front of that. So it becomes plus 4. Right? And then I keep going. I'm going to have minus 12 right here. And then here I'm going to have plus 12i. And that still adds up to 0. Well, 12i cancels negative 12i. That's kind of nice. And what I'm left with is negative 4x, and then here I have 4 minus 12, which is really just negative 8, adds up to 0, and now I can solve for x. X is equal to negative 2. Amazing. It comes out really, really nice. So I'm going to put negative 2 now in that first slot of my vector. Okay. Everybody with me? Feel okay with that? Let's come back over here. So I have my eigenvector that goes with that eigenvalue. Do I need to go on to the second eigenvalue yet? Or do I have anything else I should be doing right now with what I have so far? So technically right now, technically what I have is a solution that looks like e to the 1 plus 2i times t times this vector, which was -2 and then 2i and then 2 minus 2i. That's basically where I'm at. That's kind of where I'm at. What am I supposed to do with that? Seth?
You can find the second.
By doing what?
By swapping the signs and all of the ones that argument.
Okay, I can find another solution, so. I can do that by, so I'm gonna scribble this over here, guys, you don't need to write this down though. What I'm writing down now, you don't need to write down, but Seth is right, I could conjugate my eigenvalue. And of course, we learned that what we have to do to find the corresponding eigenvector is to conjugate the eigenvector as well. So this would be another solution. This is what you were talking about. So the trouble is, both of these solutions are unsatisfactory because they have I in them. So does anybody remember how do we get rid of the I? Floy, the Floy process. And when we're doing the Floy process, the key thing is you actually do not need to use the second solution. You'll be able to get both of your solutions just from this one. Right, so let's just remember how this works. Now we can come back and take notes on this. I can rewrite this as e to the t, and then cosine of 2t plus I times the sine of 2t. That's how the e to the I theta works with the Euler formula. It turns the exponential into cosines and sines. And then with this eigenvector, I need to break it into a real part and an imaginary part. So -2i and 0 and 2. And then plus I times, I guess it's 0 and 2 and -2. So it's going to look like that. Hey Ryan, can you do me a favor? Can you take that trash can and prop this door open with it just to get a little better airflow in here? I'm not sure they turn on air on the weekend. It's really warm in here to me. Thanks. Once I've done that, now I can Floy it out. Oil, but it's turned into Floy. So what I'm gonna get, guys, is e to the t factored out of everything. And then I have to do the first and the last together, like I want to group those together. So for the first one, I would have cosine of 2t times the vector -2, 0, and 2. And then don't forget on the last term, you're taking I times I, which actually is a -1. So you'll see a minus sign there. And then you have sine of 2t multiplied by the vector 0, 2, and -2. So there's the first and the last part. Okay, and then on the outer and inner parts, there will technically be an I. And then we still have e to the t. But this time we take the outer part, which is cosine of 2t times the vector 0, 2, -2. And then plus the sine of 2t times -2, 0, and 2. Just like that. So this is the outers and the inners. And so this whole, did I do it right?
Sorry, did we have to put the imaginary?
We're going to get rid of it now. But
Oh, okay.
technically it is there. When I do the outers and inners, that I really is there. But at the end of the day, guys, I'm gonna build my first solution, x1 of t, just out of the first and the last. Right? And then for my x2 of t, guys, I'm gonna do the same thing with the last part, but I'm gonna omit the I. So don't keep that imaginary number in your answer or you will not be happy with it. You have to get rid of it, okay? So this is x1 of t right here. and this is x2 of t right here. I know it looks like a magic act, I'm just dropping the I, but on Tuesday in class, I derived that you'll always be able to get rid of that I if you really do use the second solution. So we don't need to rehash that every time, we can just go straight to these two answers. Okay, are we so far so good? So far so good on this? Questions at all? Yeah, go ahead, Kathleen.
I
Kathleen?
had a question for the e to the t of cosine 2t plus I sine 2t, the up one.
Oh, this one, yeah,
Yes,
uh-huh.
Is that just memorization or did you? like-
Yeah, I mean, basically, so you're gonna wanna know the Euler formula for e to the I theta. This is how we're simplifying it, right? We're
Yeah.
using that exact equation, so I'm doing that here, but see the one part, the 1 times c, that's getting pulled out as the real term, and then this is coming from the Euler formula where the theta is actually the 2t.
Okay.
With the I in front of it. Does that make sense?
Yeah, thank you.
Great question. Yes, Seth?
My question is, were you gonna give us the Euler's formula for the test, or we have?
This one?
That?
Oh, you better know this one. Yeah, this one really goes way past Math 250B. Like this will get used. I can't imagine how many classes in this university that this formula would be important for. So this is one to definitely write down, or to make sure you know.
Okay, so
Yeah.
it's not given to us, we're gonna have to memorize it.
You need to know it, you need to know it. They should have, I don't know if they do this in the calc sequence, but they definitely should have that, no? Never saw it before? Oh my gosh, okay,
I'm like, I know it.
what's that?
In physics, we use it all.
In physics, you use it all the time, right, for sure, and I'm sure in the advanced engineering classes, that would be used very regularly. So this is not one that you wanna have to look up, yeah, make sure you know that one. Eric, did you have your hand up?
Just confirming the last line that we have there, the
Yeah.
minus 2t, or minus sine 2t.
This one, yeah,
It's a minus sign because the I sine 2t multiplied with the I in the vector, making a -1.
two i's multiplied together makes -1. So that's actually always gonna be a minus, right? Whereas over here, you're always gonna end up with a plus. Good point, absolutely. Other comments, other questions? Are we done with this problem?
No.
Heck no. There's another eigenvalue that we have to not forget about. By the way, if you guys really make sure you learn this Floyd thing. If you look at every sample test, you're gonna find a problem about it on there. And I always have, every time I teach this class, somebody will come onto the exam and they'll just stop with this as their answer. Right? That's coming up way short. It will get very little credit. You really need to be able to Floyd it out into the cosines and sines. So first and last makes a solution, the outers and inners makes a solution. I know we just learned this a few days ago, but keep practicing it, right? It's actually not that hard. You just have to get in the habit of what's involved there. Okay, there is another eigenvalue. What was the third eigenvalue, guys? I've already lost track of it. -1, okay. So for -1, I'm gonna have to do another null space. So I'm gonna add 1 to the main diagonal, so I have 0, -4, -2, and then -4, -4, -6, and then 4 and 8 and 8. Okay. So we have to do some calculations here to find an eigenvector that goes with this matrix. I can cross off a row for free. Any suggestions which row to cross off? There's actually no correct answer. Any of the three would be fine. It doesn't really matter. I might cross off the middle row this time, just because the bottom row just gives me this nice 4, 8, 8 turns into 1, 2, 2. And then the top row already has a 0 at the beginning of it, and I kind of like that. So I'll keep rows 1 and 3, and I'll reorganize them like that. It's not so bad. again, if we want, we can just do the AB trick to write down the slots of our final vector. We've got, these are the actual equations. If I label my columns with x, y, and z, x plus 2y plus 2z equals 0. And I can, maybe I will just use the AB trick. Is that all right? I mean, in this case, it's not hard to just set up z as a free variable and then solve for y. It's not hard. It's going to be, I think, -1/2 of t, something like that. But I don't mind just using the AB trick. So I'm going to take these two numbers, I'm going to swap them and do a sign change. So I'll do a 2 and a -4. And once I've done that, now I have to solve for x by just plugging in what y and z are. So x plus 4 minus 8, I believe, adds up to 0. So I think x has to equal 4. So that should be my vector 4, 2, -4. And so I can make my third solution now, which will be e to the -t. Right? I'm using lambda equals -1. So e to the -t and then times this vector. Put that down like so. And just make sure that's looking somewhat correct. Yeah, in my solutions, I don't have quite this same vector, but guys, any multiple, any scalar multiple of this correct answer will simply be another correct answer. So depending on how you did it, some people might have decided they want to cut this down by a factor of 2 before they do anything else. Well, that's also fine. 0, -2, -1. You could have done that. It's not a big deal. But this is fine. And now am I done? I should probably write down a final answer, which is the general solution. So the final answer, to really get 100% full credit, I should write down the final answer, which would be C1 times x1 of t plus C2 times x2 of t plus C3 times x3 of t. And I am fine with you just writing that down and not filling in the x3, the x2, and the x1 again, just because it's a lot of writing. If you don't want to rewrite all of this again, you can just sort of shortcut the thing and just write this down. But just make sure you write it down. I want to know that everybody in this class understands that the general solution requires me to build a linear combination of the individual solutions. That is an important step. Okay? Yeah, Ryan?
How did you get the 2 and -4 for the AB trick?
The 2 and the -4 here. So I'm playing the little trick on these two numbers. So I'm going to swap these two numbers, which would make -2 and -4, and then I do a sign change on one of them. So, right, so if you have A and B like that, the vector that you make is something like this. It's just a shortcut. Did that answer your question? Okay. Anybody else have a question? Yeah, Eric.
So let's say you're trying to find the null space, right?
Yeah.
And let's say after plugging in the eigenvalue,
Uh-huh.
you get a row of zeros. You still cross a row out, or is that the line
That row of zeros that you ended up with is the row you get to cross off.
Okay.
You don't get to cross off an additional row. Unless the other two rows are multiples of each other, in which case you could cross off a second row. Sometimes, guys, sometimes two rows will cross off. It's not unheard of, but the only thing you're guaranteed is that one row can be crossed off. That actually reminds me of another common mistake that I see. Let me go back to my silly little example here. If this is my null space. So I'm about to, I should be using a red pen because this is gonna be something you don't want to make a mistake with. I see students will do this. They'll say, oh, the first two rows are multiples of each other, and I will see them cross them both off. You cannot cross them both off. You can only cross one of them off, because if you cross both of them off, you're actually losing information that would guide you in calculating that null space. So yeah, just only crossing one of them off. So I would need to maybe leave this one or something like that. Okay. Good points. All right, so this example kind of showed us a lot. Any questions on it? Yeah, Arlene?
So when we were given like a solve with the X,
Uh-huh.
the A, we automatically know we're solving for the general formula.
Yeah. I mean, I think in the handout it says find the general solution, but I'm just trying to save a little bit of writing.
Oh, okay.
Good question. Okay, I'm gonna jump to something else if that's okay. Are we all good? Let's jump to something else. Is it 5 o'clock?
No, it's more.
Well, it's 4:03.
Oh my God. Am I really going that slow? Okay. Oh, it's 4 o'clock. Okay, good. I'm jumping around. I'm gonna jump to something totally different now for a few minutes, guys. I'm gonna go to the last problem on the handout. It's one of my favorites. It's actually something you did in the homework. And I just want to bring it back into the forefront because it's been a while. This has to do with linear transformations. So this goes back to chapter 6 now. If T goes from V to W is a 1-to-1, so 1-1 linear transformation. And we have some vectors. It's a set of vectors v1, comma, v2, comma, v3 is Li. So if that's a linearly independent set, then show, so this is also a theoretical problem, show that if I take the set of T of v1, T of v2, and T of v3, that this set is still Li. This is not always true. Normally, if you start off with some linearly independent vectors and you transform them under some random transformation, normally they could become dependent afterwards. But when T is 1-to-1, that's the key assumption here. When T is 1-to-1, that won't happen, and the resulting vectors, they will still be Li. And I'd like to show this one. Do you remember doing this problem? It was weeks ago. It was probably around Halloween time, so it's been a while, but it's been long enough that I wanted to do it again because I really, really like it. Actually, we did this problem in class, I think. Pretty sure we did it in class. Can somebody remind me what 1-to-1 means? Because I'm always thinking about partial credit. If I don't know how to do the whole problem, but I can write down the relevant information. Brian?
Kernel is equal to 0.
Nice. The kernel of T is equal to 0. That is exactly right. So a 1-to-1 transformation has a kernel equal to 0. Remember that there's another concept, which is the onto property. So this is not really for this problem, but just to remind everybody while we're thinking about it, T is onto just means that the range of T is equal to the entire W vector space. And there are connections between the kernel and the range that you will want to be very comfortable with. The general rank nullity theorem, right? The dimension of the kernel plus the dimension of the range adds up to the dimension of V. That's the key relationship there. So anyway, for this problem, we really just need the 1-to-1 part of it, okay? And I'm going to try to show that these vectors, T of v1, T of v2, and T of v3 are Li. Does anybody know how I'm going to show linear independence of this set of vectors? Like, how am I going to set that up? Normally, when you're showing linear independence, you're laying your vectors into the columns of a matrix and you're looking for free variables or not. But here, this is abstract. We don't have specific vectors in mind. I don't have slots. I don't have polynomials. I don't have anything. It's just abstract notation. So this is going to force me to give a proof that is more conceptual. It's not going to be calculated with a matrix at all. Instead, we have to remember sort of how to set up linear independence. And so this is actually also a nice review of something that's a little bit older. When you want to test a set of vectors for being Li, you have to assume that they cancel out in a linear combination. So you have to start this problem, guys, to start your solution by assuming, right, that C1 times T of V1, I'm building a linear combination of my vectors. C2 times T of V2, and then C3 times T of V3. I have to assume that that cancels out. By the way, guys, I'm not looking at the original vectors yet. Not looking at that yet. That is part of my assumption, but I'm showing this thing over here. That's why I'm focusing on it. I want to show that the transformed vectors are Li. So I put the transformed vectors into a linear combination. And what is it that I'm going to try to show?
That they cancel out?
That the
Wait, no,
constants-
sorry.
Eric?
Yeah.
Constants equal to 0.
That the constants are all equal to 0. That is exactly what we need to show. I need to show that C1, C2, and C3 are 0. So we'll show that C1 equals C2 equals C3 equals 0. Actually, to be totally honest with you, I probably would not put this question on this exam because it really is going back to chapter 4. This test is not supposed to really be about chapter 4, but I could definitely put it on the test next week. And there's enough good stuff in here that it's worth reviewing right now. Okay, so we have to remember the kernel and one-to-one and all that jazz. Anybody have any knee-jerk reactions with this equation I've written on the board here? Is there something that we can naturally do given that we're working with a linear transformation? So in other words, can I do something here on this left side that's kind of just a natural thing anytime you have a linear transformation? Michelle?
Do you know the close of the emission in grade 2?
You guys remember, you're on the right track. Yeah, if T is linear, it respects everything. Addition, scalar multiplication, linear combinations, you name it. It's going to respect this expression. So you can actually pull the T outside of everything. Yeah, so we can completely put the T on the outside of the whole thing. Ah, okay, so there we go. T of that whole thing is equal to 0. So what do we have here, guys? What do we have? We have a vector that is getting transformed into 0. So T of whatever this is in here is adding up to 0. What does that tell you about the vector that's inside the input of this transformation? If it gets transformed to 0, what do you know about that vector?
0 vector?
Not quite. We are going to get to that conclusion eventually, but I don't know that yet.
Hmm.
If we transform a vector, guys, and we get 0, what do you know about the vector? It lives where? Seth? It's in the kernel. Yes, that is the point, right? So the kernel of T, that would actually have been another good thing to write down. If I was fishing for some partial credit here, I would probably want to write down, well, what is the kernel of T? That is the set of vectors, V and V, such that T of V is equal to 0. So this is what the kernel of T is. It's those vectors that get transformed to 0. Well, right now I'm looking at a vector that is getting transformed to 0. So that vector C1 times V1 plus C2 times V2 plus C3 times V3, yep, it lives in the kernel of T. It lives in the kernel of T. That's very true, just from the definition of what the kernel is. That's right. But on this particular problem, what is the kernel of T?
0.
We already wrote it down. It's 0 because T is 1 to 1. It is 0. So this vector, if it's in the kernel of T, it must be 0. It must be 0. In fact, let's write that down. It must be 0. So thus, C1 times V1 plus C2 times V2 plus C3 times V3. Yep, that must be the 0 vector. Okay, so let's just go back and reflect a minute on the question. T is a 1-to-1 linear transformation. I already used the 1-to-1 assumption. I already used the fact that T is linear, right? And the original vectors, V1, V2, and V3, they are also Li. Have we used this yet? I don't think so. We have not used the fact that the original vectors are Li. In fact, we don't even really have the original vectors in a single equation by themselves anywhere on this board. But we do on this board. Notice the T is gone. The T is nowhere in this last step that we wrote down. What we have instead, guys, are the vectors V1, V2, and V3. And what do we see here, guys? We see that they are canceling out in a linear combination. But they were assumed to be Li. That means the only way they could cancel out in a linear combination, which is what's happening here, the only way that could have happened is if the constants are all 0, right? So since V1 and V2 and V3 is Li, then C1 and C2 and C3 are all equal to 0, which is what we said we would show. Right? That's what we said we were going to show, and we just did it. We just did it. Okay, what do you guys think? Any questions on that? It's a conceptual problem, really, from the beginning, but I like that problem a lot. Okay. So far, so good. Put an asterisk to yourself to come back and review this one, especially next week, because it really does tie together from chapter 4 all the way to the end. But I think it's a good one even to look at today to refresh our memory about what linear independence means. Let's do one that's maybe a little more computational that would be relevant for what we're studying for this exam, which is, I'm going to go backwards to number 9 on the sheet now. I am going out of order. By the way, I'm not going to finish this whole sheet today. That's why I'm doing another session tomorrow. But I'll get as far along as I can. So number 9 just says consider T going from M2 of R to P2 of R via T of the matrix A, B, C, D. So I'm going to plug in a 2x2 matrix. And I'm going to spit out a quadratic polynomial, which will be A minus B plus D plus negative A plus B minus D times x squared. And part A is going to ask me to find bases for the kernel and range. Okay, very standard problem. Find bases for the kernel of T and the range of T. Okay. That's the first part of the question. And if you get a question like this, guys, you can start with either one. I mean, you can start with the kernel or the range, kind of take your pick, whatever you're more comfortable with. Remember, the kernel is a subspace of V. So if you're working on the kernel, you're going to be writing down 2 by 2 matrices. And the range is a subspace of W. So if you're working on the range, you should be writing down quadratic polynomials as you're doing those calculations. So it's just a matter of which side you want to start with. Anybody have a particular preference here?
The kernel.
You have,
Oh, sorry, just do it.
yeah, I would probably start with the kernel too. Did you want to?
Yeah.
All right. I mean, especially since we already wrote down what the kernel is, we're kind of already ready to go with that. So let's start on the solution. Let's start by figuring out the kernel of t. I like that plan. So for the kernel of t, just going to give myself a note here. I'm going to start with the kernel of t. To do that, I just have to set the transformation. So if I take t of a, b, c, d, I need to set it equal to 0. So this is just going to the definition right here, guys. T of v equals 0. This is the $1 million equation when you're figuring out the kernel of t. That's the equation you always want to have in mind. Keep in mind, this is not the number 0. This is the vector 0 in P2 of R. You might even like to help yourself out by writing it so that it looks like it has the form of the outputs of the transformations. I would probably write it as 0 plus 0x squared just to help myself out. And you can see that essentially, well, I mean, what is this transformation? We've got the equation right above it, yeah? So actually, these things have to be equal to each other. These things have to be equal to each other. So we get an equation here, guys. A minus b plus d equals 0. And then we get another equation, negative a plus b minus d equals 0. I left a little bit of room there for the c variable, which is actually missing from the output of the transformation. But technically, we don't want to forget that it really was there. So this becomes our set of equations, and what you have to do is solve this system for A, B, C, and D. And for that, you can, of course, put it into a matrix, which is our standard way of solving everything in this class. Throw it into a matrix. That's going to be your matrix setup. The unknowns here that line up to these columns are A and B and C and D, like that. We have A, B, C, and D lined up like so. Now we need to do EROs to get this into row echelon form. But actually, we can see just by glancing at it that the second row is literally just a multiple of the first row. So I'm just going to go ahead and wipe off row 2. And I've got my pivot already good to go in the first row. And so I'll circle that one. And you can see that we have 3 unpivoted columns, and those will all give us free variables, right? So B equals R, C equals S, D equals T. These are all free variables for sure. And the only one that's not free is A, and I can solve for A by just using the first equation here. If I just take the first equation and solve it for A, you can see that it's equal to B minus D. B minus D just becomes R minus C. So I'll just go ahead and make that replacement there. That's what we would have. And so now I'm going to write down my kernel of T, but I'm going to make a mistake on purpose. It's a mistake I see a lot, and I would like somebody to tell me what's wrong with this. So for the kernel of T, would it be okay for me to write it as R minus T, R, S, and T, such that R, S, and T are real numbers? Would that be okay? I just told you I was making a mistake on purpose. The question is, do you know what my mistake is? Daniel?
Is it because it's not a 2 by 2?
Exactly. Okay, good. So the vectors in the kernel should come from V which means they better be written as 2 by 2 matrices. So I have all the right values here, but it's just been written incorrectly. So let's try one more time on this. I just need to make it look like a 2 by 2 matrix. So A is R minus T, B is R, C is S, and D is T. It's going to look like that one.
What's the reason for the 2 by 2 again?
Because the kernel of T is a subspace of V, and in this case, my V is right here, it's the M2 of R. So that's the universe of 2 by 2 matrices. Yeah. Yeah, does that make sense?
Yeah.
Okay. At this point, I want to get a basis for that. In order to get the basis here, guys, what am I going to need to do? Say it again. Bust out the variables. Exactly. So I'm just going to bust out the R, and I have a 1 and a 1 and a 0 and a 0. And then I'm going to bust out the T, and I'm going to get it. Sorry, I'm going to bust out the S. It actually doesn't matter what order you bust them out in. There's no S's on the first row. There's one S in the lower left corner. Otherwise, there's no S's. And then on the last vector, I have to bust out the T, and I get -1 and 0 and then 0 and 1. That is my basis. That is my basis. You guys with me? You make sure I'm not going too fast. It's been a while, hasn't it? It's been a few weeks since we did these. So this is a 3-dimensional kernel. 3-dimensional. I'm going to write that down. Actually, because of that, because the dimension of the kernel is 3, I should already know what the dimension of the range is before I even work on the range at all. Because we have this general rank nullity theorem. I want to write it down. I can't imagine it won't be on the exam. So I should at least write it down once. The general rank nullity theorem. Let's just put that over here as part of our notes. The general rank nullity theorem. And this one says that the dimension of the kernel of T, right, plus the dimension of the range of T should add up to the dimension of V. The original vector space V, which is usually something we know. It's given in the original problem what V is. So we just said that the dimension of the kernel is 3 on this problem. We don't know anything about the range yet, but these dimensions should add up to how much? We look at M2 of R, the thing I circled up there in this question. M2 of R is 4-dimensional, right? So that's a 4 right there. That's going to be a 4. And so I already know the dimension of the range of T before I even take a breath now. Okay? So let's work on that range of T for a second. So now I'm going to come back and do the range of T. We already know that the dimension is equal to 1. It's always nice when you know the dimension of what you're trying to work on. You know how many basis vectors you should end up with. Our answer should be 1 dimension. So, but let's remember, how do we actually find the range? We have not really reviewed this yet. The range of a transformation is just the span of a list of vectors that I'm going to write down, which is just the transformed basis vectors from V. So actually, I need a basis right now for M2 of R. Does somebody want to give me what's a nice basis for the 2 by 2 matrices? Read.
Like 1 0 0 0
Okay, 1 0 0 0. What would be another one?
0 1 0 0
Okay, so this is the standard one. Next one.
0 0 1 0.
And then, of course, we're just moving the 1 around to all of the 4 slots of the vector. That is not the only basis that you could use, but it is sure a nice one. It is sure a nice one. So I would love to use it. And although there are 4 things listed here, we should never make the mistake of assuming that it's 4-dimensional. And in fact, we just said a moment ago, it's only 1-dimensional. What that tells me is that when I list these 4 things out here, they are mostly going to be linearly dependent on each other, right? That's how 4 vectors in a list can be only 1-dimensional, is if they're all just scalar multiples of one another, yeah? That's what I'm just kind of thinking ahead. This is what's going to happen. I haven't actually calculated it yet, but I have a feeling that that's what's going to happen. Let's try it, guys. Let's try it. Let's actually work these things out. T of 1, 0, 0, 0. If I go back to the formula and I plug in 1, 0, 0, 0, I'm putting a 1 for A and a 0 for everything else. So if I do that on the output side, a 1 for A and a 0 for everything else, it looks to me like it's 1 minus x squared. Of course, now I'm working on the range. The range is in the W side of the transformation. So now I'm working on I'm ending up with the polynomials here. Okay, so over there we have the 2x2 matrices and the kernel. And now here we're getting these quadratic polynomials. If I plug in the rest of these, if I go 0, 1, 0, 0, I'm going to get -1 plus x squared. If I put in a 1 for C and a 0 for everything else, I actually just get nothing. And then when I plug in 1 for D, I get 1 plus x squared. And now we look at what we ended up with, and it should be pretty convincing that this is only 1-dimensional, even though I have 4 things listed, right? The 4th thing, oh, I made a mistake. Did I not? On the D variable, 1 minus x squared, not plus, minus. Yeah, that should be minus there. Okay. But what I hope everybody agrees with is that you would never spend $4,000 on a basis for the range of T. The 4th vector is the same as the 1st vector. You don't want to buy that one twice. You certainly don't want to pay any money for the 0 vector. And the 2nd vector is just the negative of the 1st vector. We don't need that one either. Guys, this is our basis right here. That is the basis for our problem. Ryan?
You would have to write it out as 1 minus x squared, or could you write it out as like 4 in front, like 1 common negative?
It would be better to write it as a polynomial. I will take off, just like over here, if you write your kernel as a bunch of slots, that's not the correct format. I will take off for that. I would take off for this as well. If you don't write these as quadratic polynomials in your range of T, technically they're not in the right universe. So be careful with that. Make sure you're always clear on what your V and your W is. And so in this case, we should write polynomials down. Daniel?
Would we be able to use the column space to get that?
Column space, the concept of the column space, great question. The concept of the column space applies to a matrix transformation. A matrix transformation is a transformation. Let me remind you guys about that. This is something to review if you need to. But a matrix transformation is only relevant when you're talking about transformations from Rn to Rm. There will be an M by N matrix that represents it. And in that case, in this setup, which is not what we have here, but in this setup, the kernel of T and the range of T are related to those subspaces we learned about earlier. The kernel, so does anybody remember which one was the kernel?
Null space.
The null space of the matrix, exactly. And what about the range?
Column space.
That was the column space, exactly. So these are really good things to know when you have a matrix transformation. But that's only the scenario when V is equal to Rn and W is equal to Rm. Here, we're working with polynomials and matrices. This is not a matrix transformation, so I can't really talk about the null space and column space of A because I don't even have an A at all in this problem. Right, it's a good point though. Go ahead, Eric.
Can you explain why we crossed out the -1 plus x squared again?
This one?
Yeah.
It's actually just the negative of this vector.
Oh, okay.
So, it's a scalar multiple of a basis vector, so it would be LD with that vector. You want to get rid of those dependencies. The other reason we got rid of it is that we already had advanced knowledge that the dimension of the range was only 1. So we knew that out of these 4 things, we should only be keeping one of those vectors. Yeah. Other questions on this? This is just part A, actually. Okay, part B should be quick. Let's just see how you guys are coming with this. I want to know, is T 1-to-1 onto both or neither? So that's part B. Is T 1-to-1 onto both or neither? So remember that 1-to-1 just means the kernel of T is 0. And onto just means that the range of T is the whole W. We actually have already calculated the kernel and the range, so we probably can just directly answer the question. However, I would like to pretend for a minute that I hit my head on a rock and I forgot what the kernel and the range were, and I just am starting from scratch again. Would we be able to rule out any wrong answers just from looking at the question alone before we do any of this other work? So this is something to review for sure. If you look at the individual dimensions of V and W, based on how those numbers shake out, which one is bigger than which one, you can rule out 2 of the wrong answers. So what is the dimension of V here, guys? 4, right? So the dimension of V, 2 by 2 matrices is 4. And how about the dimension of W, which is the quadratic polynomials? That's only 3, right? Guys, if V is bigger than W, then what do you know as far as what answers would be wrong here?
It would not be onto.
Gotta be careful with this
I
one.
mean 1-to-1.
So
It
right,
cannot be 1-to-1. When V is bigger than W, it cannot be 1-to-1, right? So, V is big, W is small. It could be onto, because you're just trying to hit a smaller circle, so that's possible. But it cannot be 1-to-1, and therefore, of course, it's also not both. Of course, we already knew that it wasn't 1-to-1 just because the kernel was not 0. The kernel was actually 3-dimensional here. So it's definitely not 1-to-1. Is it going to be onto? I don't think so. Look at the dimension of the range. It's only 1, and if we compare that with W, which was 3, right? So the dimension of the range is only 1, the dimension of W is 3. They're not going to be equal to each other, right? Onto means the range of T would have to be equal to W, which means the dimensions would have to be the same, and they're not. They are not. So I would be crossing off onto. The correct answer here is neither. I wrote down in sort of 3 bullet points way back when I wrote down those facts about this. So if V is bigger than W, then can't be 1-to-1, right? If V is smaller than W, by the way, I'm being a little sloppy to write it like this. You can't talk about one vector. I really mean the dimension of V, the dimension of W. But anyway, you guys know what I mean. Can't be onto, and if V is equal to W, then it is either both or neither. Those are the only choices. Catherine?
Do you say why it wasn't on to again?
Why it's not onto, sure, absolutely, so onto would have meant. Just the definition of onto is that the range of t would need to be equal to W. But when I look at what W, the sort of the dimension of W, and when I look at the dimension of the range, they are not equal. So that's why, right?
How do we know that the dimension of what is 3?
P2 of R, right?
Right.
The dimension of, actually, so if you remember, the dimension of any polynomial universe, Pn of R, this goes back to when we first studied some of these vector spaces, it's always just n plus 1. So for P2 of R, the dimension of it would be 3.
Okay.
Yeah.
Thank you.
Seth?
So if the dimensions match, it's automatically onto, or is there more to?
If the dimensions of V and W match, or if the dimension of the range, oh, you mean this?
Yeah.
Yes, if the dimensions match, they must be equal.
Okay.
Yes, so you can't have two, when the entire universe is W, if you have a subspace that is as big as W dimension-wise, it must be the whole W. Yeah, that's a good point. One mistake I often see people make with this, so everybody, I assume, is going to learn this, a word to the wise, you should know this, but what I see people doing with it that's sometimes wrong is people will have an example on the exam where V and W are not the same dimension. And so then what they'll say is, oh, well, therefore it's not both or neither. So in other words, they think it has to be either just one-to-one alone or just onto alone. Guys, keep in mind, neither is always in play. Neither is always an option. It's an option here or here or here. So these are arrows that are going kind of from left to right, but if V does not equal W, it doesn't mean that it can't be neither. And here we have a beautiful example of where it was neither. V is not the same dimension as W, but it turned out to be neither. So just remember, neither is always an option. You can never take neither off the table right away. Okay, you have to actually do the calculations for that. Nice, okay. So far, everybody doing okay? Hopefully. Let's do something else, maybe.
I think I just have one last question.
Yeah, go ahead.
So for the dimension of the kernel, that doesn't really specify that kernel equals 0, because we can't have a 0 dimension, right?
The only thing that is 0 dimensional is the 0 subspace.
Also, the kernel dimension-wise and vector-wise both have to be 0.
They would both be 0, yeah, in
Oh.
that case, for a one-to-one transformation.
Oh, thank you.
Yeah, absolutely true. Absolutely true. Okay, let's do another problem, guys. Let's do, I think I'm gonna go do number 4. The one thing I haven't reviewed yet is anything from chapter 8, which I do need to do, but chapter 8 usually goes a little easier for people. But so before I do chapter 8, I want to do one more thing from chapter 9, actually. So I'm going to do problem 4 next. That's okay. I'm just kind of picking the ones I think would be a good mix of stuff to look at. And so let's solve. I'm going to go back to x prime equals a times x, where A is the matrix -2, -1, 4, and then 0, -1, 0, and then -1, -3, and 2. And there's actually an initial value here. I'll put this over on the side because we're not going to work on it right away. But x of 0 is given to me as -2 and 1 and 1. Okay. So we see our good old x prime equals ax. That is the stuff we've been doing more recently in chapter 9. What's the first thing I'm going to want to do?
So the eigen.
Say it again.
Solve the eigenvalues?
Yeah, find the eigenvalues. Absolutely. I'm going to try to find the eigenvalues of this matrix. So let's jump in with that. Determinant of the matrix that I get when I subtract lambda off of the main diagonal. Okay, so I'm just going to subtract my lambda all the way across the diagonal. And in order to evaluate this characteristic equation, which is what this determinant is giving me, can somebody suggest how to solve for the determinant here?
Back to expand the middle row.
I see the zeros. I want to look for those. That earlier problem we did had no zeros in it. That was kind of nasty. But this one does have, well, on the earlier problem, I gave you a hint about what the lambdas were. Here I didn't do that. So I'm going to expand according to Reed's suggestion on row 2. So I'm going to do a row 2 expansion where I see the -1 minus lambda here. And then when I do the corresponding cofactor, I have a 2 by 2 submatrix, right, of the outside 4 corners. And I'm going to use my 2 by 2 determinant formula, right? So I hope everybody is totally good on this. See, if you're good on this, then you don't have to study it for the final. You already know it. There's the formula for the determinant of a 2 by 2. So AD minus BC. So I'm going to use that here. -2 minus lambda times 2 minus lambda, and then minus -4, which I'm going to rewrite as +4. Now, what you do not want to do is just multiply it all the way out. That'll give you a cubic equation, which potentially could be hard to factor. The better thing to do is if it's already sort of partially factored with the -1 minus lambda out in front, just leave that part alone and let's work on the part that's actually in brackets, which would be a quadratic expression, yeah? Let's just see how that would shake out. If I multiply out the part in brackets, not the part in front, just the part in the brackets, I see a lambda squared, I see a +2 lambda and a -2 lambda, which goes away. And then I see a -4 and a +4, which also goes away. I actually think that's it. Your quadratic is super simple. And we are going to set this, as always, equal to 0, as we do so many times. So what are my lambdas?
0, 0, negative.
0 and 0 and -1, and thank you for saying 0 twice. It was repeated twice, and we should write it down twice. Do we know yet whether this matrix is defective or not?
No.
Not this time, because it possibly is defective. I have a repeated eigenvalue. The issue here is, does it pull its weight? So I'm going to have to check that. And whenever I have this doubt going on, and I don't know if it's going to work or not, or if it's going to be defective or not, I always start with the repeat lambdas first. Oh, by the way, before I even go on, it is worth 2 seconds of your time to make sure that the fun facts are true. If you look at the trace of this matrix, go back up here and I add up the main diagonal, it adds up to -1. So your 3 lambdas should add up to -1. And if they don't, you should go back and try to get it fixed so that those lambdas are correct. Also, well, it's not obvious, but the determinant of that matrix is actually 0. And when you multiply these lambdas together, you do get 0. So that's all kind of fitting with what the lambdas are that we got. So I feel pretty good about what they are. Okay. But yeah, since there's a repeated lambda, I'm going to start with that one. Lambda equals 0 first. We're going to do this one first. Okay. So let's look at the null space of the matrix that we get when we subtract 0 from the main diagonal of A. Well, that means I'm actually just writing down A again. I'm not really subtracting anything. So I'm just going to write down A as it was given to me. That's the matrix A minus lambda I. It is just A itself. Okay. And I am actually feeling like I want to put the bottom row on the top and maybe do a sign change to get a 1 into the upper left corner. And then I'm going to make a pivot in the middle row by just throwing in a minus sign. But I'm crossing off a row as I always know that I can. This is another example, guys, where you could have crossed off any row and it would have been A-okay. But I don't want to cross off the middle row because the middle row is so nice for me to have in my matrix when I'm solving my null space. So I would cross off either the first row or the third row. I kind of like getting my pivot to be a 1 really quickly by doing it this way. So if we label our X, Y, and Z, notice that Z will be free. I'll call it T. And Y, if we look at the middle row here of the null space matrix, 1 times Y actually has to add up to 0. So Y is going to be 0. And now I have to solve for X. I do that using the top row. The top row, if I want to write it out, it's just X plus 3Y minus 2Z equals 0. And I already know that Y is 0. So this term is going to be gone. And so X is just equal to 2Z. And so I'll write that up here as 2T for X. Okay. So let's get our vector written down. We've got a vector here, V, which is 2, 0, and 1. And do we know yet whether this matrix is defective or not?
Yeah.
And what's the answer?
Yes.
Yeah.
It is defective, right? It is defective. So this eigenvalue of 0 showed up twice over here and only produced 1 eigenvector. Now, we can write down one solution to our system, the x1 of t. Of course, it would be e to the 0 times this vector. So it literally is just that vector right there. So that's the first solution, but we have a problem, which is that we ultimately have to get 3 solutions. And this eigenvalue is not pulling its weight, so we're not going to get a second solution directly from the eigenvectors. Instead, we have to do that W stuff that we learned just this past lecture. This is what I call the mixed eigenvalue case, because you notice we have 2 different lambdas. One of them was repeated and it did not pull its weight. Yes.
I had a question that someone asked me, but I wasn't sure how to answer it.
Okay.
If we had 2 eigenvectors and we wrote down the x1, would the
Yes.
second one have a t in it or no?
That is a great question. Guys, if this eigenvalue did pull its weight, then what would the second eigenvector be? Well, it would just be, you know, something like that with it, also with e to the 0 in front of it, and you do not put a t on it then. In that case, you don't use the W stuff that we just learned on Thursday. So you just go C1 times e to the lambda t times B1, and then the second one would just be the same e to the lambda t times B2. And there's no need to stack t's, there's no need to do the W technique that we just learned a few days ago. This would be it.
Thank you.
It would be actually very easy, and it almost feels too easy. And so people sometimes do get tripped up by that, right?
Can we add V1 plus V2 to the same bracket?
And make one single vector out of them? No. Well, no. Because this constant and this constant are not necessarily the same. So I could factor the e to the lambda t out, But I would not be able to just combine V1 and V2 together because that would cause me to lose terms. Right now, I see two terms here that are being added together. If I combine the V1 and the V2 together, then I will only have one term there. And that would not work. So keep in mind, the C1 and the C2 are arbitrary constants, so you don't want to combine those terms. Yeah, right, good point.
So that's if we don't use W's because we get two vectors from there being two.
Right, that was Arlene's question is, well, what if the eigenvalue did pull its weight? Then I wouldn't need to do the whole W shenanigans that we learned last week. We could just write this down as the answer. I love all these questions, guys. Thank you for asking them. I'm glad that we're taking our time to go through this and get things cleared up. So let's go ahead. Now that we know that it's defective, I now know that my x2 of t is going to be e to the 0t, just one, times w1 plus t times w2. And the first thing I would write down, now, technically in theory, you guys all turned in, I looked, I think almost everybody turned in homework 23. So everybody has done this, but I sometimes find on this exam that people just didn't really quite learn it yet on the homework. So practice these a little bit more before Tuesday. The first thing I would do is I would draw this diagram every time. Just start off with the diagram in front of you. So this is A minus lambda I and A minus lambda I. So I just want to review this one more time tonight, okay? In this case, the lambda is 0. So really this is just A and this is just A. There is no subtracting lambda I off of anything. But we are going to choose the W1. And what do we know about it? We know that it should hop through the use of the matrix A over to W2, but if we hop twice, we should get 0. I actually need to square this matrix. Actually, one reason why I always have one of these on my midterms, basically, I'm not trying to hide this from you guys. You can pretty much guarantee I'm going to ask you one of these problems. One of the reasons I do it is I want to know who knows how to do matrix multiplication. Right. So if you're still a little shaky on that, no, don't be shy about it. Just come ask me to review it with you. I'll do that in my office hours anytime you need. So I have to actually take this matrix and square it. So I have to square this matrix out just by multiplying it by itself. Okay, so let's just make sure everybody in this room is going to hopefully do this matrix multiplication correctly on our exam. And we do that by taking dot products of the rows of the first matrix with the columns of the second matrix. Yeah. Okay, so I'm going to quietly work it out. And if you guys want to fill in the 9 numbers, and then you can check what I have on the board, and we'll see if we get the same thing. Yeah, so this is what I got for the A minus lambda I squared. Okay. You know, this is just one small part of the problem. If you got this wrong, I would probably cry for 30 seconds after grading your paper, but I would get over it. I would get over it, and then I would ask myself, okay, but based on their matrix, were they able to then do the W business? So try not to lose sleep over this. This isn't something you should spend that long on, but you're looking for a vector that will not survive this matrix. but it should survive the original matrix. Does anybody have a good choice for me? That's what we're gonna call W1. Anybody want to throw a vector at me? Somebody besides Reed and Seth. You guys have had a lot of airtime. And I know you know it, but is there anybody who is Yasmin? 0, 1, 0. Is that what you were gonna say? Is that what you were gonna say, Seth? Is this what you were gonna say?
I was gonna say 1, 2.
You were gonna say 1, 0, 0.
That's what I was.
You were too. Okay, interesting. So we have a little disagreement here. A little disagreement. Remember, you're looking for a vector that actually will not survive this matrix, right? So the trouble with 0, 1, 0, and it happens to the best of us, don't worry, Jasmine, I've done this too. If you put 0, 1, 0 here, what'll happen is it'll pick off the second column. And the second column is not 0, 0, 0, right? So when you're playing with these kind of vectors and you multiply them up against a matrix, it picks off the column of that matrix that has the 1 in it. So this vector right here will pick off the second column. This vector here would pick off the first column. And actually the first column is all zeros. So the W1 would not survive that matrix. So I actually am going to choose 1, 0, 0. Now that is not the only right answer. Actually, you could have used 0, 0, 1 instead. But I like to pick something that's as easy as possible. Now W2 comes by taking A times W1. That's how this diagram is supposed to be understood. So here's A. If I put my W1 vector, which was 1, 0, 0 right next to it, it's going to pick off this column, yeah? Which is -2, 0, and -1. And remember that this W2 should be an eigenvector. If we look back at the eigenvector that we wrote down a couple minutes ago, this one is looking really good. It's actually just a scalar multiple of the eigenvector we already know. So that's encouraging. We should not change this. Just live with it the way it comes out. So if those negatives are there and you don't really like them, that's kind of too bad. You just have to live with them. Yeah, they have to stay there as part of your answer. But then I can go ahead now and write down x2 of t. It's going to be W1, just 1, 0, 0, plus t times W2, which was -2, 0, and -1. So this would be my second solution. So I've got x1 and I've got x2. Okay, so far so good, guys? All right. And normally there would be an e to the lambda t in front of this, but we're still working with lambda of 0. So on this problem, there is no exponential in front of this at all. Right. Okay, then we have one more lambda value to go, maybe just to kind of save a little bit of time on something that's not such a big deal. I could just give you the, is it okay if I just give you the eigenvector that goes with this eigenvalue? This one's gonna pull its weight. We know that. So we just need to do our null space thing and we can figure it out. I think I'll save a little time by actually just giving it to you here. It turns out that this eigenvector is 9, -1, and 2. So you can check this one. If you're looking for a little extra practice, you'd be able to check that. That's what you get. And so my third solution, x3 of t, is going to be e to the -t, and then multiplied by this vector, which is 9, -1, and 2. Okay. And so we can now, assuming I did that correctly, which I'm just going to take my word for it, we can write down the general solution now, which is going to come by doing a linear combination of those three solutions. So x of t equals c1 times 2, 0, 1, which was what x1 was, plus C2 times x2, I'm gonna put x2 right here, 1, 0, 0, plus t times -2, 0, -1. And then finally, we have to do a plus x3, which we just worked out. So C3 e to the -t times 9, -1, and 2. This turns out to be the general solution here. Okay, so everybody comfortable with that? By the way, it's okay to just write C1 times x1 plus C2 times x2 plus C3 times x3. However, on this problem, you're going to be better served by writing it all the way out. Why do I say that? Why is it good that I wrote out all of the terms explicitly rather than just my abbreviated answer? Read?
You're gonna have to line them up with it. When you plug in the initial value.
There's an initial value here. This is not the end of the solution. Exactly. We are solving not just for the general solution, there is an initial value right here, guys, that we haven't done anything with yet. So technically, we're not done yet. I need to take this general solution and solve for the constants. And it'll be easier to do that if I've fully written out the terms rather than just this kind of sketchy abbreviation. So what we have to do, guys, is we have to now do one last thing. And that is, we have this initial condition that they gave us. X of 0 equals -2 and 1 and 1. And what we have to do here, guys, is we need to plug in 0 for t into this thing and see what we get, right? So we have that this is equal to, well, C1 times 2, 0, 1. And then on the second term, I do have a place where there's a t, but I'm going to put in 0 for that. So on the second term, I have C2 times 1, 0, 0. And then on the last term, I have C3. Here's an e to the -t, but that'll become a 1, right? E to the 0. And so then we just get times 9, -1, and 2. So something like that. And this is supposed to basically be what we need to solve for C1, C2, and C3. We're going to get a particular solution now. It's actually 3 equations. There's the top equation, there's the middle equation, and then there's the bottom equation, right? So we actually have 3 slots here, a top slot, a middle slot, and a bottom slot. And that's going to give me 3 equations that I can work with. Read?
Can you explain how you got the third?
This one?
Yeah.
So I'm putting in 0 for t right here.
No, sorry, like getting to the vector.
How did I get that?
The 9, -1.
Well, that's why I said you have to check it. It comes from doing the null space.
Yeah, right.
Is it okay if I leave that out?
Yes.
Yeah, so I just skipped that little bit of the work, but that's the vector that we came up with. Okay, if I go across the top slot, guys, if I read everything across the top slot, you might notice I have 2 C1 on top, a C2, and a 9 C3 equals -2. And then if I go across the middle slot, I actually get -C3 equals 1. So everybody see how I'm doing this? C1 times 0 plus C2 times 0 plus C3 times -1 adds up to 1. Okay, and then if I go across the bottom slot, I have a C1 plus a 2C3 equals 1. And what you have now is a system of 3 equations and 3 unknowns. And ordinarily, I would always recommend to just now put this into a matrix and solve it. That's actually something we learned how to do in chapter 2. But this one, actually, you could kind of just wing it and get the answer. Why do I say that?
Is there already know one constant?
Yeah, but the middle equation is actually giving us a nice sort of quick answer for C3. C3 is -1. That's a -1. Right? So C3 is -1. And once I know that C3 is -1, I can solve for C1 from the bottom equation. I believe it's 3. So C1 is 3, C3 is -1. And then I have to solve for C2 as well. So this is 6, and this one is -9, which is -3. If I add that to this, I believe C2 is 2. It is 1. I'm doing it in my head. You guys can check that. That is not a big deal. So technically, your final answer, you would plug in C1 is 3, and C2 turned into 1, and C3 turned into -1. So you could actually have those values in there, and that would be your explicit particular solution in this case for x of t. That's if I gave you an initial value. The whole initial value part of it, though, is really not what chapters 6 through 9 is mostly about. Like, mostly in this chapter, we've been working on just getting the general solution. So, can I steal your handout? I have all of the pages, but they're all kind of mixed together now. Any questions on this?
I'm sorry.
1 second. Yeah, go ahead.
So only when we have repeated eigenvalues and it doesn't pull its weight, we do the W.
Correct. Yeah, that's right. This whole W business, and I just showed you a mixed eigenvalue case. But remember, what are the other cases that we learned? Super defective. And what was the other one?
Mixed.
That's this one.
Normal.
I heard the word regular defective. Yes. So there's super defective, regular defective, and mixed eigenvalue. And so this is the mixed eigenvalue example again. Good chance that I will ask you to show me that you can do this in a couple of days. So keep practicing it. I believe, actually, if you look at both of my sample exams, I'm not making any promises here, but if you look at both of my sample exams, I think there's one Floyd problem that has complex numbers in it, and then there's one of these defective systems where you have to do the W's in it. So you should definitely expect both of those things. It's definitely possible. Okay, I said I was gonna go till 5:30, I guess. I'm going to jump to a different question now. And see what we can do with this one. Let's look at number 8. On this sheet, so I'm changing subjects completely. I'm gonna give you a differential equation here, guys, so I will just abbreviate the question. It's x cubed times y triple derivative plus x squared times the second derivative of y minus 2x times y prime plus 2y equals 0. And it's asking us to find 3 linearly independent solutions of the form y of x equals x to the r. Okay. Do you mind if I just keep this for the time being? Okay. We can cheat off of that sheet there too. So I just want to be really clear about something. This is not a constant coefficient, homogeneous, linear, nth order differential equation. If it was that, if it was constant coefficient, nth order linear differential equation, of course, we would have been working with e to the rx. This is what we've always been seeing that whole thing where we do the auxiliary equation and we turn the D's into R's and then you find the roots and all that stuff. Like that is only when it is a constant coefficient, linear nth order homogeneous differential equation, which is actually not what this is. Actually, you want to really hear my confession about this. I never taught you how to solve this equation. This is not constant coefficient. You see, this doesn't have just constants. This is an x squared. This is a 2x. This is an x cubed. Those are not constants. So this is me throwing you something out of the blue that we technically never studied before. And so how could I possibly put that on a test? I can put it on a test if I give you the magic key to how to solve it, which is to try solutions of this form. So this is not e to the rx anymore. Since this is not constant coefficient, there must be some other magic form for the solutions. And as long as I give it to you, then it becomes a fair question again. All I have to do, if I have given you this, all you have to do is take the appropriate derivatives of it and plug it in and solve for r. So x to the r, we have to take 3 derivatives of that. Okay, so I'm going to start solving this now. Is everybody with me on this? Okay, so we're going to take y of x equals x to the r, and I'm going to start taking derivatives of that. The first derivative would be r, x to the r minus 1. Guys, be very careful. This is the power rule. Okay, so the power rule, if it was x to the 5th, the derivative would be 5x to the 4th, right? So this is the way the form of the power rule would go. Now I'm going to take the second derivative, which pulls down the exponent again. So the r minus 1 comes down. There's still an r there, but the r minus 1 comes down along with x to the r minus 2. And then I have to go one more time to get to my third derivative. So I still have the r, I still have the r minus 1. But now when I do the power rule again, I will have r minus 2 times x to the r minus 3. So those are my derivatives. I'm just calculating them ahead of time so that I can just go ahead and now start plugging them in on the left side. So far, so good? Let's go ahead and start plugging in to our differential equation now. I'm going to take those derivatives that I just worked out and I'm going to plug them in here. So the first term, I have an x cubed and it's multiplied by the third derivative, which we just wrote down on the left side over here. It was r minus 1, r minus 2, and then x to the r minus 3. To that, we add the next term, which is an x squared times y double prime. Well, I have that written down here also. It's r times r minus 1 times x to the r minus 2. I need a fair bit of room, don't I? Give myself a little more space here. And then I have a minus 2x times y prime, and we know what y prime is. It's just r times x to the r minus 1. And then plus 2 times y, which is just 2 times x to the r, and all of that equal to 0. It's kind of long to write it all out. But actually, it's not so terrible because if you look at the powers of x, do you see that the first term has an x cubed along with an x to the r minus 3? How do those wind up if I combine them together? Don't really cancel. X cubed, what's x cubed times x to the r minus 3?
You add.
X to the r. It's x to the r, right? So you guys all know that, right? X to the a times x to the b is x to the a plus b. So I just add those exponents. So in this case, I take 3 and I add it to r minus 3. I get x to the r. But guys, just to save a little time, if you look at the other terms after that, the same thing happens. When I take x squared and I combine it with x to the r minus 2, when I add those exponents, I will again have x to the r, right? And here, x times x to the r minus 1, I again have x to the r. And here I also have x to the r. I'm going to factor it out everywhere, right? It gets fully factored out. And now I can go ahead and put in what's the coefficients are. So r minus 1, r minus 2, and then plus r minus 1, and minus 2r, and then plus 2. All of that is set equal to 0. Looks good, looks good. This x to the r, guys, is not going to be 0 unless x is 0, but that's only one value of x. We could plug in any number for x, and this is a differential equation for any value of x. So I can just cancel the x to the r. I mean, it's not 0. At least not, it's not always 0. So we'll get rid of that part, and what we're looking at in the brackets is really where we have to put our effort to solving for r. Okay, so I'm going to try to do that. I'm going to go ahead, if you guys don't mind, I'm going to multiply this out. So I'll get, on this first term, I probably would multiply out the two the two linear factors here first. So I'd get r squared minus 3r plus 2. But this r in front jacks it up by a power of r. So I'll get r cubed minus 3r squared plus 2r out of that first term. And then I have plus r squared minus r, and then minus 2r, and then plus 2. All of that now equal to 0, just like that. And this becomes r cubed, if I simplify it a little bit. What is that? R cubed minus, this is minus 3r squared, but plus r squared, so that's minus 2r squared, right? So this is equal. And then the constant, actually the 2r cancels the minus 2r. So I then get minus r and plus 2 equals 0. Yasmin?
So, couldn't we also just factor out r minus 1 from the beginning?
From here?
Yes, so if we just,
With this one?
Yeah.
You're totally right.
Okay.
You're totally right. I wasn't assuming that I could see that off the top of my head, but if you notice that, there is actually an r minus 1 in every single factor. That is true. So I guess here's where I should just make a quick comment. If we can't get the roots of this polynomial that's showing up here, we're gonna have a real hard time showing Dr. Annan that we know how to do the problem. So you're gonna have to trust me that I'm not gonna be trying to give you, if I ask you something like this, I'm not going to be making it horrible to factor. Because that's really just a high school thing, and it's obviously something that these days you could plug into a calculator. So you have to trust me that I'm going to be reasonable about it. Now, this one is reasonable. Kind of Yasmin's already seen a really good insight into how to factor it. And even if you didn't notice that you could sort of factor r minus 1 out of 2 lines ago, by the time you get down here, you might have some idea that you sort of see like almost like an r minus 2. You kind of see that? Like if I factor, is it okay if I write one more line down here? Sure.
Mm-hmm.
If I factor an r squared just out of the first 2 terms alone, and then I factor a minus out of the last 2 terms, so this isn't quite what you were ending up with, but it's the same idea. You end up with factors of r minus 2 in both places. They call this factoring by grouping, because now what happens is you actually can pull the r minus 2 out of it. And you get r squared minus 1, and that one, hopefully everybody does know how to factor that one. It's a difference of squares. We get it factored like this. If you didn't, let's say you're on the test and you can't get it factored. Couple suggestions for you. One is double check your work, because again, it's not supposed to be something too crazy. Double check your work. Second thing would be, okay, maybe I should just pretend, make up my own roots. So let's say you didn't come up with this and you decided, I don't know what the roots are, so I'm just going to choose my own values because I can't get it factored, and you choose 3 numbers. As long as you take your numbers and then you keep going and writing down the answer from there, I can give you a lot of partial credit for knowing what to do with the roots, even if you didn't come up with the roots. Okay, so don't just give up on the problem completely. If this is like an 8-point problem or something like that, and you can't get the roots, I don't want you ending up with 0 for the problem. So take the time to tell me, or at least tell me what you're trying to do. You can take a minute and write it down so that I know that, okay, you're not getting the roots to work out. That's really a high school issue. But I mean, it's not something I taught you, right? I didn't spend any time teaching you that here. It's nothing to do with 250B is what I'm trying to say. So I don't want to have your grade on my exam be bad because of stuff that's not 250B related, obviously. So this would be, anyway, these are the roots that you're supposed to end up with. And so you're supposed to get 3 solutions here, guys. The first one is x to the first power. The second solution would be x to the negative first power. And the third solution would be x to the squared power. That would be it. And if I wanted to check if those were Li, what would I need to do? Because it does say find 3 linearly independent solutions. How do I check for linear independence in this context? Maybe you remember it's just one word that I'm looking for. Starts with a W.
Wronskian.
That's it. It's the Wronskian test. You guys remember the Wronskian? You might have to do this, right? So the Wronskian test would be where you take the determinant. Actually, we had 2 different Wronskians that we learned. There was one in chapter 8 and then another one in chapter 9. This one is going with chapter 8 because we're looking at a scalar, a set of scalar functions. The way this works, guys, you just lay your vectors into that first row. And to calculate the Wronskian, what we have to do, if you remember, we take derivatives down the matrix. So I would be taking derivatives down the matrix here. So 1, and then this would be negative x to the negative 2. This would be 2x. So just taking derivatives. And then I would have to do it again. You have to keep doing it until it becomes a square size matrix. So the derivative of 1 turns into 0. And then when I take the derivative of negative x to the negative 2, I'm going to get 2x to the negative 3. I'm using the power rule. Just taking the derivative using the power rule. The derivative of 2x is just 2. So there's your 3x3 matrix, and we would need to take the determinant of this. Remember, all we have to do is find one value of x that makes this not 0. And so we could try, if we want to gamble a little bit, we could just try a value and just stick it in there and see if we can get the determinant calculated quickly with specific numbers. But what is the easiest number normally to plug in?
0.
Actually, the easiest number normally to plug in, it would be 0, but some of you are probably 3 steps ahead of me already. I can't plug in 0 here because this is actually x to the negative 1 is 1 over x. So this isn't even in the domain of our function to plug in 0. So we shouldn't use 0, but the sort of the second easiest number to plug in, especially if you don't have a calculator, might be to plug in 1. So if I did that, let me just see what happens. When I plug in 1 for all of my x's, I'll get a 1, a 1, and a 1 on the first row. And on the second row, I'll get a 1 and a -1 and a 2. And I'm putting in 1 everywhere. The third row, I'll get a 0 and a 2 and a 2. Okay, so there's my little 3x3 determinant. And I could use the arrow method here. I think that's for a change of pace. So I'll just do that. So we recopy the first 2 columns here, and we start drawing our arrows. First arrow gives me -2. Second arrow gives me 0. Third arrow gives me 2. Then I go the other way with subtraction, -0, and then -4, and then -2. So those are the numbers I'm coming up with. And I believe that that is -6, which is not 0, which is what we want. Okay, so that confirms, since the Wronskian is not 0, that confirms that my solutions, which were x, 1 over x, and x squared, that is Li. That is linearly independent. By the way, if I had gotten 0 here, if I plugged in a number and I do get 0 for the W, what am I probably going to want to do next? Try a different number. Exactly. I would probably say maybe I got unlucky with that choice. You only have to find one value of x to sort of win this game, right? To show that these vectors are Li, you just need one value of x to work. So if the first value that you plug in doesn't work, I would probably try another one. If you try that one and it doesn't work, maybe you try a third one. If you've tried about 3 different x's and you're not getting anything to work, if you're getting 0 every time, you might have to, at some point, conclude that maybe the vectors are LD. Maybe they're actually LD. In that case, you won't be able to show that they are linearly independent like you wanted to. That would just mean that you got to kind of go back to the drawing board on figuring out solutions to your system. But anyway, these are Li. We got it on the first try. And so what is my general solution? In other words, these are the basis solutions. So this is going to be, guys, the general solution is where we write out the linear combination with the c's in it, the constants. It's just going to be c1 times x plus c2 over x plus c3 x squared. That's the whole thing. There's no vectors here. Most of the problems tonight, we've had slots everywhere. We've had all these slots that we've been drawing and filling out, but this is a scalar problem. These are just scalar functions. This is in chapter 8. I guess I should at least mention, because this is a third order differential equation to begin with, because it's third order, the solutions form a 3-dimensional vector space. So that's why I really am honing in on getting 3 linearly independent solutions. They would form a basis. It's the right number of solutions to have. We've got 3 of them here. And if we just make sure that they are Li by using our Wronskian, we know that they would span the whole solutions as a basis. So that's the point. Okay. If this was a 4th order differential equation, if it was 4th order and these were the only solutions I had, they wouldn't have been a basis yet. They might be Li, but that's fine, but they're not a basis if there's only 3 of them and I'm talking about a 4th order equation. I did that once on my exam as a true false. I think I gave people a 3rd order differential equation, and then I wrote down 4 solutions. And I said, is that a basis? Easy question. The answer is no. It's not the right number of solutions, right? An nth order differential equation should have n basis solutions. This is a theorem that you would have written down in your notes. Always good to know. Isn't that so true? It's one of the big themes of this class. It's good to know what is the dimension of what you're trying to work on. If I'm trying to find solutions to a 3rd order differential equation, that is a 3-dimensional vector space. So I should be looking for 3 solutions. It's exactly what I got here. Yeah, awesome stuff. Awesome. Okay, I've done number 8, number 9, number 10, number 11. Number 10 I didn't do, but it's like number 9. I'll do it tomorrow night. I did number 3, number 4. There's a lot of stuff here I didn't go over yet. Guys, I promised I was gonna stop, and I probably should. I have done about half of these problems, but there are some that I haven't. Let me write down the ones on the review session that I have not done yet. I have not done number 1 or number 2, or number 5 or number 6, or number 7. Number 7 is really not a big deal. And technically I haven't done number 10, but that's okay. So let me just tell you what my game plan will probably be. I will probably work on a lot of these on my next review session tomorrow. 1 and 2 are theoretical problems about eigenvalues and eigenvectors again. We actually did a little on that at the start of the review tonight. And number 5 is about the phase portrait. So I did not talk about this tonight. I'm just trying to let you know what I did not cover. So I did not talk about the thing, you remember how, I should get this camera over here. You remember how when you have a 2x2 system, there's going to be 6 possible phase portraits. You could have a saddle, a source, a sink, an unstable spiral, a stable spiral, or a circle. And it just depends on whether the eigenvalues are real or imaginary, and then whether they're positive or negative. Okay, so that's pretty recent material. I'm gonna trust you guys will study that up a little bit. The main thing I didn't do though, number 6 actually has, there's 6 parts to this problem. I have no idea why I thought I could do all of that, but I didn't. Anyway, this is about solving nth order differential equations. So the 2 main techniques that are here that you definitely need to be ready for would be the annihilator procedure. I did not go over that tonight. And also, if we don't know how to annihilate the function that's in the right-hand side of our differential equation, we learned a second method called variation of parameters. And there are a couple of formulas on variation of parameters that you would need to make sure you know. Maybe I should write those down really quickly here. The other choice would be, for anybody who wants to stay for another 20 minutes, I could do a little bit on this. Either that or I will do it tomorrow night. The variation of parameters one is just to remind you, your particular solution is u1 times y1 plus u2 times y2. So you have to know that. And then you have to know the formulas for the u1 and the u2. So there's a Wronskian. We just talked about the Wronskian a little bit. It shows up in the u1 formula and in the u2 formula. So, so there are the formulas for the u1 and the u2, which you do need to know. The capital F is on the right-hand side of the equation. The y1 and the y2 are the basis solutions to the original homogeneous differential equation. Would you like me to just quit and stop now, or would you like me to maybe do a couple of parts of number 6 where we review the annihilators and variation of parameters? I only mention that because chapter 8 is going to be, a good chunk of this exam, 25% anyway, at least. So you will get questions on that. If you feel comfortable on it, or you just want to wait till tomorrow, that's fine. But you're all here now. Would you like me to go a few more minutes?
Yeah.
Sure. It's okay. If you need to leave, it's fine. If you've got plans, but I will go ahead and do a couple of parts of number 6 on this handout. For those of you who are interested. Let's do. We'll do a couple parts and then that'll make it a little easier on me for tomorrow. Let's do 6C. So I'll do part C of number 6. And that is this problem here. Y double prime minus 8y prime plus 17y equals e to the 4x times the cosecant of x. Okay. So we see that there's no vectors here. So we're not talking about a system of equations. This is not a chapter 9 problem at all. But it is differential equations. It must be chapter 8, right? So it's a chapter 8 question. And what's the order of the equation?
2.
Second order, right? It's not homogeneous. This one is constant coefficient. So because it's constant coefficient, step 1, you really can just turn the derivatives into powers of bar and write down the auxiliary equation. This is what's called the auxiliary equation right here, guys. And it's just a quadratic, but it does not factor nicely. I would actually need to get the roots by using the quadratic formula for this. Please do that carefully. I always get shivers when people are getting the wrong roots to these things because it just makes it very hard. It's also not fun to grade papers when the roots are wrong. So try to get these roots correct by being very careful with the quadratic formula. 8 plus or minus the square root of b squared, which would be 64, minus 4ac, which would be 68. And this is all divided by 2. And just to clean that up a little bit, 8 divided by 2 is 4. And on top, I'm looking at the square root of 64 minus 68. Well, that would be -4. The square root of -4 is what?
4i. I mean 2i, sorry.
2i, which then gets divided by 2. So it becomes 4 plus or minus I. Yeah, those will be the roots. And based on those roots, can we write down the so-called complementary function here? Do you guys remember this is where you just take the roots and turn them into terms of your general solution? What would be the first term that you might write down here?
C1
Go ahead, Arlene. C1 times
cosine
cosine of
4. Or no,
I think the phone doesn't think you have it right.
yeah, I'm
Actually,
like,
what that is, that's my battery's almost dead. I forgot to bring another. Well, the review will end with me saying, and the answers to the midterm are, and then the phone will die. No.
I forgot what happens to the 4.
Okay,
actually,
so
yeah.
somebody would have confidence they know what the right thing is to write down. Go ahead, read.
The e to the 4x cosine x.
That's right. E to the
Okay.
4x cosine of x, exactly. And then can somebody else give me the next term?
Okay, I think I know now.
Okay, you can do it.
C1, 2, sorry, C2,
C2.
e to the 4x
Uh-huh.
sine x.
There we go. Okay, I like that. I would put this in a box before I do anything else. I'd get that thing circled. This first part right here, guys, that is y, what I will call y1 of x, and then the second part over here is the y2 of x. So you have these two solutions, and that is that is step one of my 3-step process that we learned for this. For step 2, we either have to try the annihilator method or we have to try the variation of parameters method. And sometimes they won't both work. They may not both work. So we have to be careful about annihilators versus variation of parameters. Which of those methods do you think we're going to use here?
Now we're gonna use.
I'm gonna
the
give you guys a second to think
variation
about
of
it.
parameters.
Remember, for example, that the variation of parameters method is never used for third order equations or higher because it's too hard to do it by hand. So at least in this class, I will not give you a variation of parameters problem that is third order or higher. Well, this one's only second order. So it could be used potentially here. Could we use the annihilator method if we wanted? Roman, why not? Exactly. If you look at the table of annihilators, which I realize we probably don't have in front of us right now, you will have it in front of you on Tuesday. The annihilator table has nothing about cosecants in it anywhere. We don't actually have an annihilator for it. So we are going to be stuck using variation of parameters. Absolutely stuck using that. And so I already kind of gave you the generic write-up for this over here. The variation of parameters method involves U1 and U2, and we have formulas for them here. So I actually like to start by finding my Wronskian because the Wronskian shows up, the W is in these formulas. So it's a good thing to do first, just so you get it out of the way. And that's going to be a determinant. This is going to be a little messy, actually. I'm not looking forward to this. We have e to the 4x cosine of x on the first row, along with e to the 4x sine of x. Those are the y1 and the y2. But I have to take the derivatives of those, which will require product rules in both slots. So the bottom row of this matrix is going to get a little bit ugly. First term times the derivative of the second plus the second term times the derivative of the first, right? So we'll have negative e to the 4x sine of x, and then plus 4 e to the 4x cosine of x, and then I don't have nearly enough room. I'll have to write the other slot down here on the bottom. Again, I'll use the product rule here, e to the 4x cosine of x, and then plus 4 e to the 4x sine of x. It's only a 2 by 2, but boy, it's kind of messy. We need to kind of clean that up though. We need to actually simplify this. So I'm going to use my other board over here to do that. I have to take this 2 by 2 determinant, and I'll do it fairly quickly, guys, because it's not terribly interesting. It's going to simplify nicely, but it just looks messy at first. So the upper left corner, e to the 4x cosine of x, gets multiplied by the lower right corner, which is e to the 4x cosine of x plus 4 e to the 4x sine of x, and then minus, so this is the, the a times b, and I have to subtract the b times c. So e to the 4x sine of x times negative e to the 4x sine of x plus 4 e to the 4x cosine of x. Whew, okay. I'm going to tell you that this simplified really nicely. So if you take this blue part that I just underlined, which is, there's a cosine of x and a sine of x with a 4 and then e to the 4x. It cancels with this part that I underlined. Because notice there is a minus here, sorry, there is an absolute subtraction right in the middle there. So the blue stuff on top cancels with the blue stuff on the bottom, which is absolutely identical to it. You guys all see that? Yeah, so what's the stuff that's not so all of the blue stuff cancels. The only thing that survives is really this piece along with this piece. Let's write down what that gives me. Of course, it's still multiplied by the factor in front. So it's going to be e to the 8x times the cosine squared of x, and then minus a negative, which becomes positive, e to the 8x sine squared of x. That is your Wronskian. And if you factor out the e to the 8x, you see what happens? Cosine squared plus sine squared is 1. That's right, it's just equal to 1. And so that's all we have for the Wronskian. I said it became very simple. Becomes very simple. Okay, so that's my W. That's my W. And once I've got my W, guys, if you're with me, is everybody with me enough? Yeah. Now I can write down U1 and U2. U1 is negative the integral of y2 times f all over W. You will have a table of integrals. You have to trust me again. I'm not here to test you on integration. So these integrals should be reasonable. Either simple integrals or with your table, they should be reasonable. So we'll have negative the integral of y2. Y2 was e to the 4x sine of x times capital F, which was e to the 4x times the cosecant of x, all divided by W, which was e to the 8x. So this is the first integral that we would have to do for U1. Does anybody remember what the cosecant is?
It's like ln, right?
Oh no, I'm not talking about the integral of it. Does anybody know how to calculate the cosecant? It's just 1 over the sine. So actually, it cancels the sine right there. And then the 2e to the 4x's cancel. And so you just have the integral of -1. So you just get negative x. That's really nice. Now, if you were on the exam and you're like, oh, I don't remember anything about cosecant, and you got this integral here, and you're like, I don't know what to do with that. Keep in mind that if you don't do this integral correctly, but you have the whole rest of the process, you did step 1, you did your Wronskian, you write the general solution, and you'll get almost all of the credit for this, right? And maybe I take off a point or two, but it's not going to be terrible. So don't give up on the whole problem just because maybe this integral isn't something that's resonating with you in that moment. But I promise you, it will not be something that's supposed to be hard. It's not my goal. Let's look at U2. U2 would be the integral of y1 times f, all divided by W. So this would be the integral of, I go back over to the middle board and I see my y1, which was e to the 4x cosine of x. And I see the capital F again, e to the 4x cosecant of x. And then this is all divided by the Wronskian, which is e to the 8x. Notice that there's no minus sign on the U2 integral. So there was a minus sign on the U1 formula, but not on the U2 formula. Again, the exponentials totally cancel. The exponentials totally cancel, but what doesn't come out quite as simple this time is that when I rewrite the cosecant as 1 over sine, it doesn't fully cancel. In fact, what you end up with is just cosine of x over sine of x, which is the integral. Well, I could just write it that way. Cosine of x over sine of x. That's actually probably the best way to write it. Now, that is the same thing as cotangent of x. So you could look that up in the table if you want to. But the other way to do this is, if you didn't want to think about the table, is it's just the integral of 1 over u du. right? So if you just let u equal the sine of x on the bottom, I mean, this is how you would learn to do the integral of cotangent. You would write it as cosine over sine, and then you would just let u equal the sine of x. The du would be cosine of x. Well, the integral of 1 over u du is just the ln of u. So in this case, the ln of, actually it's the absolute value of u, which would be sine of x. Notice, by the way, I'm not adding plus c on the end of these antiderivatives. It's because you're allowed to choose c to be 0. We were only looking for one correct antiderivative. So I recommend just forgetting the plus c, just write it down as such. And as soon as I have the u1, which is right here, and the u2, which is right here, I can write down the step 2. Let's do it. Let's write it actually back over here again. So let's write it down, the final step 2 part. We're almost done with this one. The particular solution, it is u1 times y1 plus u2 times y2. So u1 was negative x, y1 was e to the 4x cosine of x, u2 was ln of absolute sine of x, and y2 was e to the 4x sine of x. That's the particular solution right there. And am I done? Why am I not done, Ryan?
You gotta put them together.
That's right. That's right. There is a step 3. And honestly, even if you didn't quite figure out all of step 1 and step 2, you should still do step 3 because, guys, step 3 is probably going to be worth a couple of points. And all you have to write down for step 3 is just show me that you know this, that you know that there is a requirement to add together the complementary function in the particular solution. So couldn't get any easier than that. Couple free points if you just write this down at the end, even if the whole rest of the thing was wrong, I can give you something for that, right? Which I want to do. So that's it. You don't need to recopy. If you're wondering, do you need to recopy all of this with all of that? No, you don't need to do that. So that's probably good enough. Any questions on this? This is variation of parameters. This is in section 8.7. All right, I think I'm going to leave it at that for now. I did not do any annihilator problems today, but I will do some tomorrow, or of course in my office hours. You're certainly welcome to, oh, you can just take that one. Okay. So I'll be happy to do annihilators with you later on. You want to stand out? It's just this thing. It's out of Canvas, but you can have it if you want a physical copy. It's fine. Thank you guys for coming.